There we go. All right, so let's go on and continue with where we left off last time. And that was right here, right? We were talking about how many tangent lines can you draw on a function between the given interval that will be parallel to the secant line that's drawn between through the endpoints of the function that is given there, right? So when we looked at this first one, right, we saw the secant line that connects from 1 to 3 is this red line right here. And I saw that there was only one tangent line that is between those two endpoints, right? We were able to draw it right there, but all I'm asking for is how many are there? And there was just one there. And we looked at number 2, right? And number 2, we're looking at the interval from 1 to 3 again, but there's something different here at x equals 1, right? At x equals 1, we have a discontinuity there, don't we? It's discontinuous at 1, right? You see that at 1, we have a hole where the function is approaching 1 from both sides, right? So the limit is approaching this value of, it looks like, I can't read that number. Is that 12? That looks like 12, right? But the function is defined at 1. So it is discontinuous here, so it draws you this secant line right here. And when I was using my ruler, I was looking for a function, I'm sorry, a tangent line. What? Okay, I was looking for a tangent line on here. So when I'm doing my tangent line here and I'm running this ruler along right here like so, none of these tangent lines as I run along here are parallel to the secant line, right? None of them are parallel. So how many tangent lines are there that are parallel? There are 0 tangent lines that are parallel to this secant line that I have drawn, right? So that's what we discussed last time. And then I had you guys, hopefully you did it for homework. You went through and you went from 1 all the way down to 10, and you figured out how many tangent lines were there. And we're going to go over as a class. But before that, I want you guys to answer for me these questions right here. This one doesn't even talk about how many tangent lines there are, but instead it just talks about, can you tell which graphs are continuous and which graphs are not continuous? So that's what we're going to do right now. So give me a second here. I'm going to go ahead and open up your Pear Deck for those of you who are in there. After you've answered this, by the way, how are you guys feeling today? How are you guys feeling? You guys stressed out? Not stressed out? Ooh, who's at a 10? Somebody's very stressed out right here. But a couple of you guys are not as, most of you guys are around here, around level 3, which isn't too bad. But ooh, if you're feeling a 10 right now, hopefully there's something else we could do to help you feel a little bit better. I don't know what that could be, but hopefully something will help you out. Also, I'm noting that there are only 23 of you guys out of a class of 31. So what's going on, guys? There's 8 of you who have not clicked on here to get into this. So let me know why you haven't done so. Why have you not clicked into this Pear Deck? Are you not able to? Can you drop the link? Of course, that makes it easier. If you were joining a little bit late, you might have missed the link. So please click on that link, get on in there. And yeah, let's go ahead and get over to the next one. Let's get on over to the next one right here. So what I want you guys to do for me right now is just type out the graph numbers that are continuous, which graph numbers are not continuous, which graphs are differentiable, and which ones are not differentiable. So how can you tell if something is continuous or not? That's what we learned before in the past, right? And we talked about this really quickly when I went over number 1 and 2 right here. Right? Number 1, I stated that this graph from 1 to 3, but this is important, by the way. You have to look at it on the interval that they give you. This graph is continuous. Whereas graph 2 is not continuous at 1 because of that hole right there. So that would be my answer for this one, right? This is a graph that is not continuous. This is a graph that is continuous. So can you guys please go through the 10 graphs that we have there and just simply answer for me which ones were continuous. Therefore, you'll also know which ones are not continuous and which ones are differentiable and which ones are not differentiable. So go through that and do that real quick. I'll give you about a minute to go through those 10 graphs and answer those questions for me. And after about a minute, I'm going to give some participation points. Well, yeah, participation points, but more importantly, I want to give you guys some cardinal points for those who are participating, right? So that's not what I wanted to open. I already have that open. I want to open up this right here to give you some cardinal points for doing this. So looking good so far. I see answers so far by, well, 3 whole students. 3 whole students. What's going on here? Oh, I lied. 5 whole students. All right, better. That's looking better. So start typing it out. You don't have to give me any reasons or anything. You just got to tell me what number graph is continuous, which then that also leads to which ones are not continuous, because you can't be both continuous and discontinuous, right? On the interval that's given. And then tell me which graphs are differentiable, right? Which graphs are differentiable. Does it have to be differentiable at all points given the interval? Yes, Monica, yes. It has to be differentiable on the interval. Well, that's what they're asking, right? They should be asking that. Which graphs are differentiable on the, look at that wording right there. Which graphs are differentiable on the open interval? Interesting. Which graphs are differentiable on the open interval? A to B. Whereas this part is asking about continuous on the indicated interval, and those symbols are drawn as closed intervals. Interesting. Let's see here. We got some numbers being answered here. We got, let's put this in alphabetical order to make my life a little bit easier. We have some answers from Brian, both Brians, Kaylee. Okay, wait, what am I doing? I was supposed to go over here. What? Oh no, is this broken? Can I not give you points right now? Do I have to do this later? PBIS reward. Can I go this way? Will this work? Can I just jump in through here without going in through Clever? No, because I have to log in onto Clever. And Clever doesn't seem to be working. All right, I'll just have to write your names down on Pear Deck and then give you guys your points later. And if I don't give you your points, can somebody send me a message or join? Yeah, send me a message later and remind me to give you guys your points. Say, hey, knock me, give me my points or I'll break your thumbs. Right? And then I'll say, oh, no, not my thumbs, and I'll give you your points. Right? So, yeah. Well, that's okay. We'll figure that out. All right, let's see here. How are we doing so far? I want to take a look at some of your answers here. Let's go by time. Let's see who we got here. So remember, if you have one that's listed that it is continuous, please don't list it as, not continuous. Can't be both. If you list the graph as differentiable, don't list it as well as to be not differentiable. Okay? They do not share that. All right. Let's see here. Which graphs are continuous? Not bad. Grace, unsure about graph 8, it looks like. Don't know if that's continuous or not, but you have answers for everything else. That's not bad. Haley, you've answered for all 10 graphs for the first 2 questions. That's beautiful. Moving on to is it differentiable or not? Fatima, good start. Graph 1 and graph 2. Oh, got another one typed in there. Nice. Emily's using complete sentences. I appreciate that. Telling me which ones are continuous and which ones are not continuous. Good. David, careful. Remember, we talked about this in class. I don't know if graph 2 is continuous, right? I think that whole, right, makes it not continuous. Juliet, I like your complete sentence as well for that first one. And then all you got to do is type in the rest, and that will help you complete your sentence. Ava's working through it. I like it. Oh, Brian, you actually did not type any numbers. You just circled the letter A and the letter B. Fooled me, Brian. Oh, Brian N, I should say. You fooled me. I thought you actually would have had more numbers there. Brian V, though, you got all 10 described already for continuous and not continuous. That's good. That's good. Looking good, guys. Looking good. Okay. All right, I got 9 people who still haven't responded, and I'm still looking at only 27 out of 31. So there's 4 of you guys who just refuse to click on my pair deck, and I don't know what's wrong. But you guys got to let me know at some point, because you guys remember that participation is 10% of your grade. You guys got to tell me why you can't get in there. Let me know. You can type it out. You can just message me about it once I get this going. But let me know why you guys can't get in there. I don't want to just be like, oh, this kid wasn't actually there and then not give you any points. All right. That being said, let's go and take a look at these graphs, and then let's answer these questions, yeah? Let's answer these questions right here. Which graphs are continuous on the indicated interval? So we talked about this, right? I'm going to, I don't have a way of writing it down. I'm just going to have to memorize this down somehow, right? So we're going to talk about this right here. Let's take a look at graph 1. I already said that this graph right here is continuous. How do I know it's continuous? There are no jump discontinuities. There's no infinite discontinuities. There's no holes, right? Removable discontinuities. So graph 1 is continuous. Graph 1 is continuous. That's right. Is continuous. All right, what can we say about if it's differentiable or not? Well, remember, differentiability just means that you can't take the derivative on that specific interval, right? And when can you take the derivative? When, if you think about it, it's just the limit definition. If you think about the limit definition of it, can you approach a tangent line calculation, right, using the slope as it approaches from left and right, right? Does the left side approach the right side when you calculate your slope? And an easy way to see that is basically if you take a ruler, right, can you draw a tangent line as it approaches that point from both sides, and does it approach the same value? So this one right here, as I approach from the left side, it's approaching this slope right here. And as I'm approaching from the right side, it's approaching the same slope. So it is differentiable at that point. And you can do that for all the points on this said interval, right? So this is differentiable on the interval, on the open interval. That's the important part, right? It does not include 1 and it's continuous, right? Including the values of 1 and 3, and it is differentiable on the open interval from 1 to 3. Remember, that's being asked in this question right here, right? It's not actually asking, is it, where am I? Over here. It's not actually asking if it's differentiable on the closed interval from A to B. It's asking if it's differentiable on the open interval from A to B. So make sure you spot the difference there, and you'll say, well, what's the difference for that? And that's over here. Look at number 2. Number 2, we can see this, right? This clearly has a jump discontinuity. So we can say that number 2 is discontinuous, right? On the closed interval from 1 to 3, right? Because at 1, at that endpoint, we have a hole there, not continuous. But this is actually differentiable, but not at 1. Differentiable. But we don't care, right? Because we don't actually look at the differentiability at the endpoints. We're looking at it, everything between the endpoints. So this is actually differentiable, right? So number 2 is differentiable because we're not looking at it at 1. We're going really, really close to 1. So when I get my ruler here and I'm drawing my tangents, as I get closer and closer to 1, I can keep calculating that as I get closer and closer, but I never quite reach 1. Does that make sense? Right? So the question that's being asked, like I said, make sure you're paying attention to this. It's differentiability on the open interval from A to B. So we don't include the endpoints for A and B when we're looking at differentiability. We only include that for, is it continuous? Is it continuous on that interval? Okay? That interval. So let's keep going. So that's number 1 and 2. Let's go to number 3. Let's go to number 3. By the way, hopefully you guys got, I'm gonna write these answers down for you as well as I'm doing this. Hopefully you guys got number of tangents for 3. I got 2. Maybe you guys got something different, but I got 2, right? And I'm looking at this graph, right? It looks on the closed interval from 0 to 3. That is definitely continuous, right? That is definitely continuous. Wow, Knockney, can you? Continuous. There you go. It's continuous on the interval from 0 to 3. And it's clearly differentiable. Differentiable. right? On the open interval from 0 to 3. There's no problems with me taking the derivative from 0 to 3 on that function, right? So I say graph 3, continuous and differentiable, right? How about graph 4? By the way, graph 4, if I was to do what we were doing the other day, right? This is going to go from 0 to 1. That's from here to here, which gives me that secant line right there, which clearly gives me one tangent line at that point right there. That's what I'd say I got for number 4. Hopefully you guys got the same thing. Can you explain in depth how they are? Of course. How they are what, Brandon? Which ones are which? Continuous and differentiable is what you're asking for? Let me answer this one first, and then I'll go into depth if that's what you're asking for. Ah, okay, you are asking for continuous and differentiable. Okay, so let's talk about that in depth a little bit. Continuous. Let me answer this one first. This one is continuous from 0 to 1, and this one is differentiable. And let's go into depth a little bit about why that is, right? So if I'm looking at this function from 0 to 1, I'm looking at it right here, right? This blue line that's curved right there. How do I know it's continuous? When you're looking at a graph, it's easiest to tell if it's continuous if it doesn't have any holes, it doesn't have any jump discontinuities, meaning it doesn't go from like here to here, right? That's not continuous. And it doesn't have any asymptotes, any vertical asymptotes, any what did I call it? Infinite discontinuities, right? So if I had an asymptote that was between here and this one went down like this and went up like that, that's not continuous either, right? So those are 3 things that you look out for that are not continuous, right? And if it doesn't have any of those, right, then you can see that you can draw this with your pencil without being lifted from point A to point B. We consider that continuous. That's why for number 4, it's continuous. And the same thing for number 3, right? Look at the blue line that's curved from 0 to 3, right? From 0 to 3, there's no holes in between there. There's no jump discontinuities, and there's no vertical asymptotes. So it is continuous all the way through. Hopefully that makes sense on what you're looking for when you're trying to figure out if something is continuous or not, right? And same thing for up here. Why was number 2 not continuous? Well, on the interval that we're focused on, at x equals to 1, we have a hole there. And we have to look at that when we're looking at continuity for the question that's being asked, right? Not for differentiability, just for continuity. And it is not continuous at that point at x equals to 1 because the function, right, the limit as x approaches 1 on this function is approaching 12, right? That's basically the idea there. As the limit gets closer and closer to 1, right, the limit value is supposed to be 12, but the function value itself is here, right? So that makes that discontinuous. That was back in chapter, I think, 2, when we were talking about if a function is continuous or not. Was it chapter 2 or was that chapter 1? Could have been chapter 1. But Brandon, does that help with the explanation of how you can find out if something is continuous or not? All right, and if not, maybe you can come and we can talk about like limit definitions of it. Okay, yeah, you got that? Okay, awesome. Now the second part that you're asking about is to go a little bit more in depth about differentiability. The easiest way that I used to do differentiability in my mind was just basically, can you draw a tangent line there around it? And if you can draw it around it, when you take the limit of those tangent lines as they get closer to that point, does it equal? And you'll say, what? So basically this. So pretend that we're not looking at this function at that tangent line right there that's parallel. So let's pretend that we're looking at this tangent line right here. Just, have you gotten pretty good at imagining tangent lines? Hopefully you have. And you can picture a tangent line, right? Oh, hey, Kimberly, sorry, no worries. Let me give you a link for our pair deck today. And you can join in and open up your notes that we did last time as well. We're finishing those up right now. We're not finishing, we're trying to finish it up. So back over here, Brandon, right? So you can picture this tangent line right up here, right? And what I'm saying is, how do I know this is differentiable at that point? How do I know that that tangent line is the correct tangent line? What I'm saying is, if I were to draw tangent lines around it, right? Like I approached it from here, and I'm drawing my tangent line like this. As I approach it from the right-hand side, do you see how it approaches the tangent line that's already drawn, right? If I move this tangent line closer and closer, it approaches that tangent line that's there. And if I do the same thing from the right-hand side, you see here, as I come in from the right-hand side, I can't, there we go. So as I get closer and closer from the right-hand side, it approaches the same tangent line. That's what it means to be differentiable, right? That you're able to draw that slope and calculate that slope of that said tangent line from both sides. So how do you know when something is not differentiable, right? Let's talk about that then. So that leads us to number 5, right? Number 5, you guys would agree, right? That number 5, based off of those explanations, I would say that number 5 is continuous, right? Continue. Can you not spell today? Oh, wait, no, you can't spell at all. It is continuous, right, from 1 to 4. There's no holes, there's no jump discontinuities, there's no infinite discontinuities. That is clearly a continuous function from 1 to 4, right? 1 to 4. Now, is it differentiable? It is differentiable here, 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 but is not differentiable there, right? And that point is on the interval. Why is it not differentiable there? Because that's a cusp, right? And we talked about cusps before we went on break. Anytime a function has a cusp, not differentiable, right? That's exactly it, Brian. There has no local linearity. Hey, I forgot I taught you guys that. We could have used that to help me explain differentiability earlier, couldn't I? You could just zoom in closer and closer, and then it looks like a line. I like it. So this one is not differentiable on the open interval from 1 to 4. So hopefully number 5, you put that one down. You're able to write that one down into that list that you have. All right, let's keep going. Number 6. Oh, by the way, I don't know if you guys are able to see this. There is no way you can draw a tangent line that is going to be parallel to this. And I was always fooled by this. I was always like, knock me. There's a point there. Why can't you just draw this tangent line like that? That looks parallel. I would say that there should be 1 there. But why not? Just because it only touches that function at one point, that doesn't actually make it its derivative or its / tangent line, even though it's a single point. That's why cusps are weird. Do you know what the tangent line looks like as it approaches the cusp? Do you guys know? Do you guys remember? If you come from the right-hand side, the tangent line is actually approaching a vertical line as I get closer and closer to this point from the right-hand side. And as I get closer and closer from the left-hand side, it's getting closer and closer to a vertical line as well. So that tangent line, yeah, it isn't straight. If you zoom in enough, it'll forever be a cusp. But if you keep approaching it closer and closer to that point, right, that tangent line is going to approach this slope right here, which is a positive infinity slope, whereas this one's going to be approaching negative infinity slope, and they don't approach each other. That's another way of thinking it as well. But yeah, I like the whole non-local linearity, right? So that's why there's no tangent lines there, because of that cusp. All right, let's take a look at number 6. Number 6, from 0 to 2, that is clearly discontinuous, right? Discontinuous. Would you guys agree? You guys see why it's discontinuous? At what point do I have a problem for this function to be continuous here from 0 to 2? At 1. That's right, Monica. At 1. That's right, Brian. That's right, Brandon. At 1, we have a jump discontinuity, clearly not continuous. Secondly, this is also not differentiable as well. Would you guys agree? From 0 to 2. Where do you have the problem with differentiability? I'm just kidding. I think you guys already know, right? I can't take the derivative at 1 as well. You guys see that? If I try to take the derivative at 1, as I approach from the left-hand side, I end up with a slope that is going to be 0. And then when I come from over here, I'm going to end up with a slope that's going to be towards infinity. And at the same time, well, you just can't take the derivative there. You zoom in, there's not going to be a line that's drawn there, right, at x equals 1. So no local linearity there either. So that's number 6. 6 is not continuous, and it's also not differentiable. Let's go here. 0 to 3. 0 to 3. I didn't actually draw this one out right yet. All right, knock me. You can English. Right there. Right. There's my. There is my secant line, right? And 0 to 3. 3 has a dot there, so it does include that point. And I would say that I can draw a tangent line here, right, that looks somewhat parallel at about here at that point, right? My sketches are a little bit off today, but that looks like it matches. I'd say this one, you guys hopefully got this as well. There's one tangent line there, right, that is parallel to that. And of course, I'd say that this is continuous, right, on the open interval from 0 to 3. And this is differentiable from 0 to 3. And you got to be careful with that, right? I'm not looking at it exactly at 3 when I'm looking at differentiability. I'm looking at it as it approaches up to 3. You see that? There's a difference there. All right, how about this one right here is going to go from 2 to 4, right? Which is right there to right there, which is going to give me this secant line right here from 2. Wait a second. I drew that wrong. 2 is over here, knock me. 4 is over here. There we go. That's a little bit better. So that gives me this secant line right there. And I'm hoping you guys can see, I don't see any tangent lines that are going to be parallel to that, right? That one's going to be too steep, too steep, too steep. And then this is going in the positive direction. No way that's parallel, right? Hopefully you guys agree this is going to be discontinuous, right? And not differentiable. I'm going to speed through this a little bit here. So hopefully for number 8, you guys are able to write that down. It looks like you guys are able to see it, right? 8 is discontinuous and not differentiable. Number 9, I'm going to say number 9 is continuous, right? And it is differentiable. And number 10 is continuous, but it is, wait, where is that part of the interval? It is going from -4 to 2. Yeah, that negative one right there is not differentiable, right? So hopefully you guys were able to get all those. Did you guys do all right? Did you get the same numbers? Did you, any of them tricky for you guys to understand if it's continuous or not? Or any of them tricky to figure out if they are differentiable or not? Because that is actually an important part of the mean value theorem. You need to know which is which. Does that make sense? Can you guys let me know? Type into the chat. Are you guys okay with that? Does that make sense? Does that not make sense? All right, so we're going to go and count the numbers that were continuous here real quick. Let's see here. We're going to start with 1. So 1 was continuous. 1, 3, 4, 5, 7. 1, 3, 4, 5, 7. 1, 3, 4, 5, 7, 9, 10. So 1, 3, 4, 5, 7, 9, and 10 are the ones I have to be continuous. How'd you guys do? You guys, all right? That kind of makes sense. That leaves me with the ones that were not continuous was 2, 3, 4, 5, 6, 7, 8. 2, 6, 8 are the ones that were not continuous on that interval that was given there. Which ones were differentiable? Let's take a look through and count which ones were differentiable. We got number 1, number 2, 3, 4, 1, 2, 3, 4, 7, 1, 2, 3, 4, 7, 9. 1, 2, 3, 4, 7, 9. Right? So that leaves the other ones that were not differentiable to be 5, 6, 8, and 10. 5, 6. Why is 7 continuous? Let's take a look at 7. Why is 7 continuous? That's a good question, Monica. Right? Because you want to say this right here, huh? That jump discontinuity looks iffy, doesn't it? But here's the thing. At 3, the function is defined to this point up here. So the limit here, this is actually continuous at that particular point because of the interval. But no, that's a good triggering question there that you saw, right? That you're like, that's clearly a jump discontinuity. But yeah, it's because of the interval. We're only focused on the interval that they're telling us to look at, right? We're not looking at the function as a whole. We're looking at it at a specific interval. All right, so let's take a look here at other questions here. Which graphs are continuous? Which graphs are differentiables? And are there any that overlap, right? I'm hoping you guys can see this right here. Graph 1 was both continuous and differentiable, right? Graph 3 was also continuous and differentiable. So was graph 4, graph 7, and graph 9. Okay? That one contained both. Now, what does that lead me to say about these? Well, let's take a look at those graphs, by the way. I think I'm going to cheat here and just look at some of your notes. I think some of you guys should have gotten like 4 for the number of tangents for this one. This one should have been 0, right? And then we have the answers for the other ones right there. But here's the thing. Can you guys, do we have the numbers for all these? Yes, we do. 2, 1, good. And then this one here is 1 and 0. Awesome. So check this out. Can you guys look at these ones I have highlighted that are both continuous and both differentiable, and tell me, what do you notice about those answers, right? Not just those answers, but look at those number of tangents there, right? What do you notice about that? What do you notice about that? For number 1, 3, 4, 7, and 9, right? Those functions that are both continuous and differentiable. What do you notice? What do you see? Anything in particular? Was it 1, 3, 4, 7, and 9? Let's zoom out a little bit. So let's take a look here. 1, right? There's graph 1. The number of tangents this had was 1. Then the next one was 3. The number of tangents this had was 2. 4 4 was one of them as well, right? And then what was the other one? Next one after 4 was 7, right? Next one after that was 7. And the next one after that was 9. Maybe better yet, what do you notice about the ones that are not both continuous and differentiable? What do you notice about the ones that are not both continuous and differentiable? So everything else that's not 1, 3, 4, 5, 7, and 9. What do you guys notice? Anything? Anything in particular? What do you see? What do you spot? Anything at all? What do you notice? Let's go again. Graph 1 was one that we should look at. Not 2, because 2 was discontinuous. So graph 1, right? Graph 1 had 1 tangent line, right? That was parallel. How about graph 3? That's the next one that we're supposed to look at. How about graph 3? How many number of tangent lines did it have? Yeah, it has 2. And Brian's going out there and going on a limb to say it. That's right, Brian. Which ones? He's saying they don't have tangents. Be careful with the word they. Which ones don't have tangents? Which ones don't have tangents? That's what I want. 2, 5, and 10. Yeah, the ones that are not both continuous and differentiable, right? The ones that are continuous and differentiable have a tangent line that's parallel to the secant line. If it doesn't have either one of them, right? Sorry, it doesn't have both of them, I should say, right? If it's differentiable but not continuous, it has no tangent lines. And same can be said if it's continuous but not differentiable. It has no tangent lines. So what we can say is basically, if I can guarantee that the function is a continuous function on the interval that's given, and it's differentiable on there, it looks like I can guarantee that it will have at least one tangent line that's parallel to the secant line that's drawn there, right? I don't know if you guys are spotting that. If a function is differentiable and continuous, you can guarantee that it has a tangent line that is going to be parallel to the secant line. That's all I'm saying. If you can draw a function that's continuous and differentiable, the secant line that you have there, you're guaranteed to have a tangent line that is going to be parallel to that. And that's essentially what the mean value theorem is stating. It's the mean value, the average value between those two. There is a value that's between that will equal to that same slope, right? If I calculate the slope from A to B, there's going to be some derivative that's equal to that said slope. And I think that's a very interesting idea, and it's actually used a lot in speeding tickets. I don't know if you believe me or not, but if you can actually calculate how long it took for someone from point A to point B, but you only saw them going like 55 miles an hour, right? But it only took them like 5 minutes to get from one point to another, depending on how far away it is, you can actually prove that that person was speeding somewhere in between the middle, right? But we'll talk about that later. That's an application of it. But that's the idea behind the mean value theorem. If a function is continuous on a closed interval from a to b, is there a tangent line that is parallel to the secant line through the points with x coordinates x equals to a and x equals to b? If the function is differentiable on the open interval from a to b, is there a tangent line that is parallel to the secant line through the points x coordinates equals to a and x equals to b, right? It only holds true if the function is both continuous and differentiable, right? In order to ensure that the graph of a function has a tangent line that is parallel to the secant line, the function must be continuous, and that's the key word right there, and differentiable. You see that? And it was, for which functions do these two conditions hold true? It was these functions right here that we have highlighted, right? Numbers 1, 3, 4, 7, and 9. And that's what leads us to this right here, the mean value theorem. This is already in your notes, but I'm going to write it out for this video. If you're writing down your own notes, you might want to write this down. Actually, I'm going to be lazy here. I think I could just be lazy here. It's already in your notes, right? Down here. The mean values theorem is stated as followed. If the function g is continuous on a closed interval, a to b, and differentiable on the open interval from a to b, then there exists at least one x value, x equaling, we call it c. C is between a and b in this case, for which the derivative evaluated at that point c is going to equal to the slope of the endpoints, right? G prime of c is equal to g of b minus g of a over b minus a. That's just the slope formula for the endpoints. And I'm saying that the derivative evaluated at this given c, or not given c, this proven to exist value of c is going to equal to that, right? I'm going to be a little lazy here. I'm just going to copy and paste this instead of writing this whole thing down into my notes. But you guys can write it down into your own notes, right? Like I said, it's actually already in your notes. But, you know, boom, there we go. Beautifully copied, right? Here we go. So if a function g is continuous on a closed interval and differentiable, there exists at least one value of x, we call that c, that's between a and b, for which the derivative evaluated at that point is going to equal to the slope of the endpoints. G prime of c is going to be equal to g of b minus g of a over b minus a. And you're like, knocking, what the heck are you talking about? Everything that you've just drawn over here. Like, for example, let's look at one that has this one example right here. Check this out. This right here, let's call this g. This is called g of x, right? So check this out. This right here, this point is actually 0, g of 0, whatever that point is, right? Or in other words, 0, 0. This one up here, this point right there, is going to be 3, 3, or in other words, 3, g of 3, right? And all I'm stating is that this right here, this tangent line right here, this g prime of whatever the heck that point is, we'll call it c, right? At the derivative evaluated at this particular point, g prime of c, whatever the value is going to equal to, you ready? G of 3 minus g of 0 divided by 3 minus 0. I'm calculating this right here, which is the slope of this secant line, and I'm saying that I can calculate the derivative at c, and it's going to equal to that same value. That's all the mean value theorem is stating, is that that specific tangent line, it exists, right? The mean value theorem is a theorem that helps you prove the existence of that point. And what is that point? It's just a point that tells you that if you were to calculate the derivative there, it will give you the same slope as the slope of the endpoints. That's the mean value theorem in a nutshell. Okay? It's a theorem that proves an existence of a point. And what is that point? What's the importance of that point? The importance of that point is just basically the derivative at that specific point equals to the slope of the secant line of the endpoints. All right, so let's go ahead and again, this right here, let's fill this out together. This one is not filled out in your notes, so if you guys could, please copy this down and fill this out. Wait, actually, do you already have this filled out on yours? Let me see. Hold up. Oh, it's not. Good, good, good. So we actually should fill this out together, right? Fill this out together. So, there it is. Okay. The mean value theorem can be interpreted geometrically as follows. G of B minus G of A over B minus A is the slope of the line segment joining the points A, comma, G of A and B, comma, G of B. So this right here, right, is the calculation of your secant line, the slope of that secant line. G prime of C, on the other hand, right, G prime of C is the slope of the line tangent to the graph of y equals G of X at the point C, comma, G of C. I know this sounds like a little bit weird, but honestly, when you start working out these problems, you realize how easy this theorem is. All right, let's take a look here. Wait, were you guys able to copy that? I'll put that up for a little bit so you guys can copy that. Make sure you guys get that down. By the way, if you at any point I moved too fast and I moved the notes too fast, please remember, I know this is being recorded, but you don't want to wait. If you don't want to wait to watch the recording, these notes are posted live on OneNote, right? You can always click on the link for OneNote, and you can always scroll on and see what I'm writing on there on the website for OneNote there, so you can see what I'm doing. Okay. All right. So on the graph of y is equal to G of X, locate the X value X equals C that is ensured by the mean value theorem, right? Like I said, it's a theorem that proves the existence of that point, right? It's a big deal. You can prove that it does exist. Another way of stating the mean value theorem is as follows. It is if the function g is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists parallel lines, one through the points a, comma, g of a and b, comma, g of b on the graph of y is equal to g of x, and at least one tangent line of the graph of y is equal to g of x at the point with the x-coordinate x equals to c on the interval a to b. Really wordy, but let's do a problem. Let's do a problem. So this is in the notes. You can write this down on your own notes. As of right now, for you submitting, I don't need this copied down. You can copy this down on your own paper right now. So you can go ahead and submit the CAMI notes. We're pretty much done with the filling out part of the rest of that. This part we're going to do by hand. Okay, this one we're going to do by hand. So let's read this problem. For each function and interval, determine if the mean value theorem applies. If it does apply, explain what conclusions you can draw from it. And if it does not apply, state why not. So in order for the mean value theorem to work, you need two conditions to be met. The first condition, right? The first condition that needs to be met is that you need to be able to see that g of x is continuous on the interval -1 to 1. So look at the function. What's the function there? We have a polynomial function, and it looks like it is of degree 3. So this is a cubic function. And we're looking at it on the interval from -1 to 1. So for your own knowledge, or from your own past knowledge there, do you know if cubic functions are continuous or not? Or are there any problems with cubic functions? And hopefully you guys can see that. Cubic functions are just these functions that do this, right? They either curve up or they either curve down, depending if they're positive or negative. And the numbers there just make them more wavy or less wavy. And there's no real discontinuities there. So I can go ahead and make this claim, right, for this first condition. This function, g of x, is going to be continuous from -1 to 1, right? That's the first condition that needs to be met. You need to be able to show that it is continuous. And sometimes just saying like, oh, it's a cubic functions are continuous for all real numbers, that's more than enough. Most of the times when it's continuous, there's not much really to say. It's only when it's not continuous, and you can actually prove that it's not continuous. And we'll talk about that on the next example there. So let's go back over here. Second thing you need to prove, Second thing you need to prove. First thing is continuity. Second thing you need to prove, or not prove, you need to state, I should say. You don't need to actually prove it. You just need to state it, is that the function also needs to be differentiable. Differentiable on the interval -1 to 1. But remember, continuity means that it has to include the endpoints. Differentiability goes up to the endpoints. It does not include it. So since g of x is continuous and g of x is differentiable, how do you know this is differentiable? Just try to take the derivative of it and see if you can, right? Oh, let's see if I can take the derivative of this without having any issues. 12x squared minus 2x. Looks differentiable to me, right? Since I can say that it is differentiable, I can state that the mean value theorem works. And how does that get stated? I'm going to write that out as there exists C such that G prime of C is equal to G of B minus G of A all over B minus A. If you want to put that into words, well, I mean, it's already in words, but without the equation that's there, I can state that the mean value theorem says that the slope of a tangent line is going to equal the slope of the secant line of the endpoints. There you go. That's the conclusion that we can draw from this, right? If we can show that a function is continuous on the interval that's given and it's differentiable on the interval that's given, there has to be a point that's in there where the derivative is equal to the secant line. Sorry, the slope of the secant line. I keep misstating that. The slope of the secant line. Okay? How you guys doing? You doing all right? Hopefully you are. If not, let's actually do it as a calculation. Okay, let's do it as a calculation. So I'm going to put this problem over here to the side, and we're going to do this as an actual calculation. Okay, so let's actually do a calculation here. So let's take a look here. Let's say I was given here that function g of x, right? 4x cubed minus x squared plus 4 on the interval -1 to 1, right? And you got to check if you can use the mean value theorem. And we already checked that we can, right? It is continuous, right? So let's write that off. It is continuous and it is differentiable, right? On the interval from -1 to 1 and on the interval from -1 to 1. So since these both check out, I can use the mean value theorem for this problem. So here's the actual how we do the math to calculate this, yeah? So let's actually do the work here. You ready? So looking at the function that they give us and this right here, this is my A value and this is my B value, I can actually calculate the slope of the secant line. The slope of the secant line is going to be equal to G of 1 minus G of -1 divided by 1 minus -1, right? So we plug this in. So the slope of the secant line is going to be equal to the function evaluated at 1 minus the function evaluated at -1. So I have here, right? Let's take a look here. This is going to be 4 times 1 cubed minus 1 squared plus 4, right? That's me evaluating it at 1. And I'm going to subtract that from 4 times -1 cubed minus -1 squared plus 4. And this, of course, is being divided by 1 plus 1 because -1 and -1 just gives me, I'm just going to write that as a 2, guys. I think that's going to be fair if I wrote that as a 2. Okay, Simplifying this out, the slope of that said secant line, sec, is going to be, let's see here, 4 times 1 is 4, minus 1 is 3, plus 4, that's going to give me 7, right? Minus over here, that's going to give me negative 4, minus 1 is going to be negative 5. Negative 5 plus 4 is going to give me negative 1 over 2. So when you simplify this out, 7 minus negative 1 is going to give me 8 over 2. The slope of that said secant line is 4. The slope of that said secant line is 4. You ready? So what I've essentially calculated now is, if you can picture this, I've drawn this graph and I've drawn a secant line between the endpoints of negative 1 and 1, and it gives me a slope of 4. Okay? Now what I'm saying is, with the mean value theorem, I can calculate a value that's between negative 1 and 1 that's going to give me the same slope. But how do I calculate the slope of tangent lines? I need to find the derivative. So take the derivative of your function, and let's write that out. The derivative of 4x cubed is going to give me 12x squared minus 2x plus 0. By the way, sometimes functions get a little more complicated, but this is us applying derivatives now. Does that make sense? That's why we're doing this. We learned last chapter how to calculate derivatives. Now we're applying what to do with these said derivatives. And this is one of the things you can do with it, is to calculate the said mean value theorem. Now I'm stating this. The mean value theorem says that I can have g prime of x be equal to the slope of the secant line. Well, what's the slope of the secant line equal to? It's just equal to 4. So I can write this out. 12x squared minus 2x equals to 4. Now this becomes a nice quadratic equation, and I just need to solve, when does this happen? When does this occur? What x values does this occur at? So I'm going to go ahead and solve this quadratic using, I think I'm going to use factoring. I'm not going to use the quadratic formula, but you could use the quadratic formula on this one if you wanted to, right? Because it is a quadratic equation. 12x squared minus 2x minus 4, set this equal to 0. I'm going to go ahead and use the zero product property to try to solve this by factoring it out. I'm going to first factor out a 2 and reduce this down. Make this as 6x squared minus x minus 2, right? Factor this out using the whatever method of factoring you remember, right? Box method. If you had me, you might have learned the Korean method, the guess and check method. Whichever method you need to still remember how to factor. This stuff does not go away. If you don't remember how to factor, you could use the quadratic formula. You're just, it's a little overkill. Anyways, if I factor this out, this should be 3x minus 2 times 2x plus 1. And you ask me, how do you do that in your head? It just takes practice. I know that the factors of 6 is either going to be 1 and 6 or 2 and 3. And I just guessed 2 and 3. And then the factors of negative 2 is going to be 1 and 2, 1 positive, 1 negative. And you need to make sure that it combines for your inner to make the negative 1x. So that's going to give me negative 4x. This is going to give me a positive 3x, and that gives me the negative x. That's how I know that works out. It just, again, it just takes practice, right? Anyways, using the zero product property to solve this, 3x minus 2 is equal to 0. 2x plus 1 is equal to 0. And go ahead and finish this off here and solve this. I'm going to have this over here as 3x is equal to 2. So x is equal to 2/3. Over here, I have 2x is equal to negative 1, and I end up with x is equal to negative 1 over 2, which means the c value, where my tangent lines will be, is going to be equal to, right? Not parentheses. It's going to be equal to negative 1 over 2, which is between negative 1 and 1. So this is a value that's okay. And the second value that's going to be there is going to be 2/3, and that's also between negative 1 and 1, so that value works out as well. So that's my answer. What I've essentially found is the point, which I already know exists by proving the mean value theorem. I'm getting ahead of myself. By the mean value theorem, right? But you can actually do the math and calculate where they occur as well. But I think the bigger deal is proving that it exists. But doing this actually shows you where you can find it and find out where it exists. I'll give you guys a second to copy that down. I kind of want to show you this graphically. Right? I want to show you this graphically. Let me see if I have this still. But I think it's kind of neat to actually see it. So check this out. Okay, check this out. Let me Let me write this function in right here real quick. This is 4x to the third minus x squared plus 4. Okay. We're looking at it from, what was the value? From -1 to 1, right? -1 to 1. So hopefully you guys got that down. Take a look at this right here. If you guys haven't played with Desmos before, I really suggest you do. It's a nice free app, right? No ads. You can download it on your phone. It takes up less than a meg, right? Now, my a value is at -1, right there, and my b value is at +1. So I'm going to zoom out so I can see both points. Can you guys see that? Can you guys see the 2 points right there at -1 and 1? Hopefully you can. All right, so it's right there. So here's -1, and here's +1. The output values are actually shown as well. Hopefully you guys can see that. Now here's what I find neat. There is the secant line that goes through -1 and 1. And we calculated the slope of this line already. You see it right here? It's actually calculated for us right here. The slope of that is equal to 4. All right, the slope of that is equal to 4. Now here's what I think is neat. I can't actually have that on there, but here's what I think is neat. The two values that we got, we have x is equal to, I didn't finish this off last time. Yeah, I didn't. So x is equal to negative, what are the values? X is equal to negative 1/2 and 2/3. I'm saying this, if I were to graph a tangent line at those points, those tangent lines will be parallel to this green line. And my skills at this is a little bit rusty, but let me see if I could code this real quick. Y minus, I think I can do this. Give me 1 second. It should be f of -1/2, right, is what we got. Right, I think so. That's going to be equal to f prime of -1/2. Hopefully I got this right. Times x. No. Times, is it x? Yeah, times x minus -1/2. Boom. There you go. You see this line I just typed in right now? Here's my tangent line. Do you guys see it? My tangent line right here? Hopefully you guys can. And this tangent line is parallel to this green line. I'm hoping you guys can see that. And yeah, that's the idea. That's all the mean value theorem is stating. All right, it's proving that that point between -1 and 1 exists where the slope of this tangent line is going to be equal to the slope of the secant line. That's all it is. It's just proving that that exists. It's an existence theorem. It shows that it has to be there. And then you could do the algebra after you do the derivative to actually calculate what those values need to be. And if I did the same thing and I graphed the tangent line at 2/3, you'll have another tangent line that looks parallel to that. We could do that real quick as well. I just have to change these values to 2/3. 2/3 right there, right? Let's put this right here as 2/3 right there. And then we'll do this one right here as 2/3 right there. And you can see it. It's tangent at that point right there, right? It's tangent at that point right there. And it's parallel. This tangent line is parallel to that green line. And that's the mean value theorem in a nutshell, guys. It proves that you can find it, and it proves that it exists, right? And then you just do some algebra work to calculate it to find it out. I say that this is what most people focus on when they do the mean value theorem, right? And it's actually not too bad. The calculations is like, oh, make sure you remember how to solve your polynomials, solve for that c. But I think what's more important is you guys understanding that it exists. I think that's a bigger deal. If you can prove that the function is continuous and you can prove that the function is differentiable, I think it's a bigger deal understanding that that function has a c value that exists between a and b. Anyways, let's go ahead and finish up these notes. I said I was going to, and then I said I was going to go into Rolle's theorem, but yeah, we got it. We got 10 minutes. I can do this. So let's take a look at this function right here. We're looking on the interval from 0 to 3. right? We're looking on the intervals from 0 to 3. So let's go back over here. Okay, let's go back over there. And let's talk about this guy right here. Is the function continuous from 0 to 3? Is the function continuous from 0 to 3? Hopefully you guys can see that it is, right? That it is. Or is it? Yes, what do you think? Is it continuous? What do you guys think? Is f of x continuous on 0 to 3? I don't have a graph to look at this time. Instead, I need you guys to tell me, looking at this function, can you tell if this function is continuous or not from 0 to 3? What's something that you can do to check to see if it is or not? In this case, it actually might be easier to prove that it's not continuous. Does anyone see an issue with the function at hand? Remember, we're looking at this function right here. Is there any number that you can plug in for x that will break this function? Vertical asymptote. Oh, you're going above and beyond there. You're stating the type of discontinuity. You're right, Monica. There is going to be a vertical asymptote. Where is there going to be a vertical asymptote? At x equals to 1. That's right, Monica. You are perfectly correct. Now, if you're like me when I was in high school and you're like, how the heck did Monica realize that x equals to 1 is going to give you an issue? Look at the function itself, 1 over x minus 1, and try to picture what will break it. What is something that is not okay when you're dealing with fractions? And I hope you guys can see fractions are not okay when you end up with 1 over 0 or anything over 0, because anything over 0 is undefined, right? 1 over 0 is undefined, meaning the function is not continuous. And when does that happen? Monica's saying it's happening at x equals to 1. Well, hopefully you can see if you plugged in 1 for x, you'll get 1 minus 1, which equals to 0 in the bottom. Since the function is undefined here and 1 is between the interval from 0 to 3, I can state that the mean value theorem does not apply. And I'm done with the problem. Does not Apple. Does not apply, right? That's it. So it's as simple as that when you're trying to show that you can't use the mean value theorem. If the function is not continuous, just state, hey, at this point, it's not continuous. Since it's not continuous and that point is in the interval, I can't use the mean value theorem for this problem. And the same thing can be said when something is not differentiable. Something is not differentiable. Okay? Let's keep going. Let's take a look at this one right here. How about this one? How about this one? Is this function continuous on the interval that's given? If we follow Monica's rule of looking at this thing and how she found the other one, you guys can probably state, hey, I'm going to end up with 1 over 0 if x is equal to -1. Do you see that? -1 plus 1 is going to give me 1 over 0, so it's not continuous at x equals 1. It's not continuous at x equals 1. But do you care about x equaling to -1 for this problem? What do you think? Do you care about x equaling -1? I mean, to be fair, you probably don't care about a lot of these problems, but this particular problem, Ava's saying no, Monica's saying no, and I'm hoping you guys can see that. X equals -1, that is right, guys. Both of you guys are right. X is not equal to x equaling to -1 is an issue, but it's not an issue we care about because we only care about the interval from 0 to 3. This -1 is not part of it. This -1 is not part of it. So all I care about is it continuous on the interval from 0 to 3. And you plug in those values, you kind of just test it. Oh, 0 plus 1 is 1 over 1. That works. 3 plus 1 is 4, and 1 over 4. Oh, that works as well. Hey, it is continuous on that interval. Ta-da! Is it differentiable on that interval? Differentiable. Is it differentiable on the interval from 0 to 3? And guess what? It is. Where is it not differentiable? It's going to be not differentiable at x equals to -1. And again, we don't care about it at x equals to -1, right? We don't care about it there. We care about it only from 0 to 3. So since it checks out, you actually can use the mean value theorem for this problem. meaning you need to calculate what is the slope of the secant line. And the slope of the secant line is going to be equal to h of 3 minus h of 0 over 3 minus 0. And if you guys are just wondering how I got that, this is my a value, this is my b value, right? I'm just calculating the slope between there. So let's do that real quick. Let's calculate the slope of the secant line, and I can then go ahead, since I've already proven that the derivative does have a value that is equal to the secant line, I can find that after I calculate this value. So I'm going to go ahead and do this right here. H of 3 is going to be 1 over 3 plus 1 minus h of 0, which is 1 over 0 plus 1. And this, of course, is all being divided by 3 minus 0, which is just 3. So that means the slope of this said secant line is equal to 1 over 4 minus 1 all over 3. And of course, you guys all love fractions, don't you? Right? Fractions are not as bad as a lot of people say they are. Right? Common denominator is 4, so I'm going to rewrite this 1 as a 4 over 4. So 1 minus 4 is going to be 3 over 4 all over 3. I'm sorry, negative 3 over 4 all over 3. And simplifying this out, this is going to be, you remember how to do this? Fraction over fractions, you keep flip change, keep the top, flip the bottom. So instead of it being 3, it's going to be 1 over 3, and then change it to a multiply. Right? That's what this changes to. So the 3's cancel out. I'm left with my slope being negative 1 over 4 for the slope of my secant line. That's not the final answer, though. That's just saying that there is a derivative in between 0 and 3 that should equal to negative 1 over 4. So we got to do the derivative of this guy. So let's do the derivative real quick. Let's go ahead and erase this out. Let's go ahead and find the derivative here. So h prime of x is going to be equal to, actually, I need to rewrite this h of x first of all, right? You guys know how to take the derivative of this? Please don't take the derivative as is. You could use the quotient rule if you want, but there's actually an easier way. If you just rewrite it to the power of negative 1, like so, we can just use the chain rule, which you guys have become masters at, right? You guys have become experts at taking derivatives using the chain rule. And if not, you should really stop by and we can do some practice problems, because you do need to know how to do the derivatives using all the rules to get through this here. So chain rule means that I can take the derivative of the outside, which is going to be negative 1 times x plus 1 to the negative 2, times it by the derivative of the inside, but the derivative of the inside is just going to be 1, right? Derivative of x is just 1. So technically it's this times 1, but times 1 is just going to be itself. So rewriting this out and cleaning it up is going to be negative 1 over x plus 1 squared. That's what the derivative is equal to. And that's what I need to set equal to negative 1 over 4. Negative 1 over 4. So doing the work right here, I'm going to go ahead and do that real quick and set negative 1 over x plus 1 squared, set that equal to negative 1 over 4. Right? Set that equal to negative 1 over 4. Cross multiply is how I would solve this problem out. I would see that I end up with, get rid of the negative signs, by the way, negative 1 and negative 1. I could just multiply both sides by a positive 1, and I can rewrite this as 4 is equal to x plus 1 squared, right? If you guys aren't familiar with how to solve, rational expressions, you got to let me know. This is stuff that's from Algebra 2, or in other words, I think it was like IM 2 or IM 3 when you should have learned this. But if not, please let me know. Take the square root of both sides when you're solving this. I'm not going to factor this out and do it again. It's already halfway through the completing the square process. When you take the square root of x, you got to remember to do the plus or minus of it. So I have plus or minus 2 is equal to x plus 1, which means that x is equal to negative 1 plus or minus 2. In other words, c is going to be equal to negative 1 plus 2, which is going to be 1, and negative 1 minus 2, which is going to be negative 3. But you only care about this one. Why don't I care about the c equaling to negative 3? Because negative 3 is not on the interval that we're focused on. All right. I've given you quite a bit and quite a lot, and I'm going to be asking you guys to do a couple practice problems for homework on calculating the c value, seeing if you can apply the mean value theorem or not. That's something that you need to know how to do, and also practicing stuff from the last section as well as your homework, okay? And that's going to be it for me today, guys. I'm going to stop it there because it is 10:37, and I've been rambling for a long time now. But if you don't get it, please stop by today during my office hours from 1 to 2. And if you still don't want to, we'll go over some more problems on Tuesday. Remember, we have no school on Monday, guys. And that's going to be it for me. I'll see you guys on Tuesday. Have a good weekend. All right. I'll see you guys later.